Hey guys, in this video I want to introduce how you can solve parametric equations using Nspire. Here we have a parametric equation that I made up. We want to graph the function, find its velocity, speed, acceleration, find dy dx, and find second order dy dx. This is going to be a longer video because we have more contents to cover, and also the way we define those functions is quite different from previous videos. Also, I want to both explain how you can get the result and also why we use the sequence of procedure, and if we did define things the other way or graph it the other way, why it wouldn't work or it would lead to potential problems. Alright, so let's get started. First we want to graph this function. As usual, we have those two functions predefined, but what's different is that instead of having f of x as before, or f of t, we now, and g of t, we now have x0 of t and y0 of t. Why is this? Well, the first apparent reason is that this is much more representative of what we're actually doing. So if you think, say for example, when you're doing dy dx, you want dy dt over dx dt, right? If you are using f of t and g of t, you might not be sure which one is actually representing x of t and which one is actually representing g of t. But if you did use x0 and y0, well, it is very apparent that, this is x position and this is y position, right? Yeah, so this is the first reason why we used x0. And you might also wonder, well, in this case, why don't we just directly use x of t and y of t? It is even more representative and it's much more efficient to type this compared to adding a 0 after it. Well, this is because maybe somewhere in the future we want to use f of x, yes. And in this case, it is quite ambiguous that, well, if you're referring this x as a variable or if you're referring this x as this function, the x of t. So that's why we used x0. Or we have to add something after x. Now you might ask again, why we use x0 but not x1, x2, x9? Well, this we do have a reason, and it's going to be apparent in just a few seconds. Just bear with me, and I'm going to introduce it when we graph the functions. Yes, so now we got those two functions defined, and we're going to graph them. We go to the graphing page, but here, this is the entry for graphing functions, right? And now we have parametric equations. So we want to switch, we press menu and press entry. We want to switch to parametric equations. Now we just put our x of t here, and, oh, I forget, x0 of t here, and what am I doing? Come on, 1 second. We have x0 of t here, and, okay, nice, finally, y0 of t here. Great. Despite this weird graph, well, now we know the reason why we couldn't use x1 of t or x2 of t. Because if you had used x1 of t or x2 of t or any number of t, then say you define x2 of t here as maybe t squared, this would actually influence what you're graphing in this entry, because now this has exactly the same name as what you define here. Yes, so that's why we can only use x0 instead of x followed by other numbers. Alright, going back to our weird graph. Well, I don't know if you guys can see it, but, well, this graph is this very, very small segment here, and it is not correct, apparently, because we know from our knowledge that since x squared plus y squared equals to 1, this should be a circle, right? And t from 0 to 2 pi should be sufficient to graph the whole circle instead of just this very small segment. We can try to increase the interval of t, maybe changing it to 50 pi. Well, now we're seeing a better curve, and if we increase it to 100 pi, we see a longer curve. But this doesn't make that much sense, right? Because from 0 to 2 pi should be sufficient to graph the whole circle, but somehow it's not. I want you guys to actually pause the video and think for a second if you guys can figure out why this is happening. And yes. Right, welcome back. I'm going to tell you guys the answer. The reason for this is actually because we're graphing in degree mode. If you look down here, it says degree. So if you actually input this as 360, well, now you have the full period or full circle. But normally, when we're doing calculus questions, we're given all of the stuff in radian, in units of radian. So we want to be able to graph t from 0 to 2 pi and at the same time get the full circle. The solution to this is to just simply change degree mode to radian mode. It is very simple on your physical calculator. This is what you will be seeing on your physical calculator. You can just press here, and it changes from degree to radian. See, now we have the full period of the circle. But it does look like it is more like a regular polygon instead of a circle. Not so smooth, right? This is because our step size is too big. We can just decrease our step size to, let's say, 0.08. And now see, you have a very smooth circle, which is good looking. And you can actually solve from question 3 from the graph, because you know dy dx at pi over 2, it starts from 0, right? T starts from 0. So at t equals to pi over 2, you know that the slope of the tangent line is 0. So we've actually solved question 3 graphically. Yes, and now I'm going to tell you how you can solve question 2, 3, and 4. Alright, now we want to find the velocity and acceleration speed at a given time. So we know that velocity is the derivative of position, and we know that acceleration is the derivative of velocity. So this is what we define on the right. This is velocity in the x direction, velocity in the y direction. Same thing for acceleration. Now if we want to find velocity at, say, t equals to pi over 3, we just type vx of pi over 3 and vy of pi over 3. This gives us our velocity in the two directions. Same thing if we want to find acceleration, we do ax and ay. And if we want to find the speed, we do square root of vx squared plus vy squared, right? That's easy. Well, I do have a bonus tip that can possibly boost this efficiency. And also, you know, you might get nervous in the test, and you know, you might just only type vx of pi over 3 and forgot to type vy and might forget a dimension. So a way to avoid that is to define a vector v, and this will be a vector that has velocity in the x direction and velocity in the y direction. So this is its first dimension, which is vx, and the second dimension, which is vy. If you're using a physical calculator and you couldn't find where to find this bracket, it is control and open parentheses. And this bracket is basically a simple way to define vectors in Nspire, and you separate the dimensions by comma. All right, and the comma's here. Yes. All right, so now after you defining it this way, you can simply type v at pi over 3, and you see you get the velocity in 2 dimensions. What is also good about this is that now if you want to define your acceleration vector as well, you can directly do derivative of v of t. And now you have your acceleration vector at pi over 3, or at any time you like, anytime the question asks. For speed, you can also do the same thing. You can define the function speed of t and define it to be the square root of vx squared plus vi squared. Yes, there is something to be cautious here, that when you're defining your acceleration, because maybe somewhere else in the integral, you might be using a as a constant. Say a might be here and b is here. In this case, it wouldn't work because Nspire is not sure if this is a variable or you're referring to this function. So a simple way to avoid that is to type a of t, or you can do ac of t instead of a of t. But, well, if you're not using a elsewhere, this is sufficient. Now the last thing for us to do is just define dy dx and second order dy dx. We do this by simply defining our function dy dx as definition. So we know this is dy dt over dx dt, right? So dy, this is y0. Oh no, what am I doing? Dy dt and dx dt. So dx x0 of t dt. We can test this by saying dy dx at pi over 2. This gives us 0, and it testifies our previous conclusion, where, you know, at this point the slope of the tangent line is 0. So yeah, this point, yes. The same thing applies for defining second order dy dx. We just do dy second order dx. Well, you can name it anything you like, but well, I like to put the 2 here. Yes, so this would just be, as definition, dy dx dt, right? So this is dy dx dt. And below is dx dt, right? So dx dt. Well, good. And if we want to find second order derivative at t equals to pi over 2, we just put this in, and this is our answer. Well, it's a long video. I hope it makes sense. And thank you guys for staying all the way to the end. And I'll see you guys in the next video.